We watched in class how we can bend water using a charged balloon, and that happened because water happens to be a polar molecule. And the next thing we're going to do now is to find out how do you recognize a polar molecule when you see one, and we'll look at several different situations. The idea is that every time we have a bond, some of these atoms are very, very, very polar, very electronegative, and they pull the electrons away from the other atoms. So these atoms, when they are part of a molecule, are usually the negative portion of the atom. And that every time there's a bond where it has one of these atoms, it makes it polar. Let's take several different examples. One example, just single atoms. The noble gases, if you see noble gases, they end up being just single atoms, and if it's just a single atom, it can't have a positive end and a negative end. It's just going to be nice and non-polar. So all of these single atoms, the noble gases, are definitely going to be examples of non-polar. And some people call them molecules because they're individual atoms, but we will definitely say that these guys are all non-polar. So if you see these examples, non-polar. They would not bend if we put them near a balloon. Now when it gets to a two-atom molecule, some of them will be polar, some will be non-polar. And the big test here is, can we look at the molecule and have two different ends on that molecule? Now if it's two atoms that are exactly the same, no matter how you draw a line, it's going to be the same on both sides. So this is definitely going to be non-polar. Same thing here, two chlorines, definitely going to be non-polar. But if we take a situation like HF, F pulls electrons more than the hydrogen does, so it ends up being a little bit negative one side, a little bit positive on one side, and so that's going to be a polar molecule. So when you see two different atoms bonded together, then that's definitely going to be polar molecule. So these two examples would be polar, and the two examples here will be nonpolar. Now when we have several atoms together, then we have to look more carefully. So here we start off with methane, CH4, and when you see methane, we can see that there's no way that we could draw a line where one side is different than the other. These two are exactly the same on both sides, so any bond dipole is going to cancel, so this would be a nonpolar molecule. So if it's very even looking, it's nonpolar. Now here's water. Now we've seen water over and over. So water molecules definitely are polar. We saw them bend in our first picture. And we can see that we can draw a line where one side is negative and the other side is positive. Now, water is a little bit tricky because we could also draw it like we do here. And when we draw it very straight, it doesn't look like it's going to be polar. So the other thing to watch for are these oxygens have lone pairs. If you see lone pairs, that usually means the molecule is really going to be bent, and that'll make the molecule polar. So even though maybe we're going to write the molecule in a straight line, we know that it really is a bent sort of a molecule like we see in our picture, and that's going to be polar. Now in the same way, we can see here we have CH3Cl. Now three sides here are hydrogens. If they were all hydrogens, it would be very, very even and it would be nonpolar. But since one side here is chlorine, so we have two different sides, this is definitely going to be a polar molecule. So if there are different atoms connected to the center, that's going to make it polar. Now here we have an example of CO2, and we can see that this molecule is very, very even looking, very symmetrical. So if we draw a line down the middle, we can see the two sides are the same, so this will be very non-polar. Some more examples. Here's NH3. Now NH3, we have this lone pair up here. That's going to make it a little bit polar because of the fact that we could draw a line, let's say across here, and if we do, then the one side is different than the other. One side has hydrogen, one side has a lone pair, and that's going to make it a very polar molecule. If we do the molecule next here, we have a carbon with 2 hydrogens and a double bonded oxygen. We can draw a line. We can see the two sides are different, and that's going to be a polar molecule. Now we have BF3. BF3, we said there is no lone pair on this portion. So we have three fluorine atoms. They are going to repel each other as much as possible, and we're going to end up having 3 atoms here at 120 degrees, and that's going to be very even, and it's going to be a nice non-polar molecule. Now we have down here at the bottom is we have hydrogen, oxygen, oxygen, hydrogen. So this is the H2O2 hydrogen peroxide molecule. And again, we can draw this 2 different ways. In this first side, you can sort of see that one side is definitely going to be negative and one side is going to be positive. And that'll be a polar molecule. This other one, we have to watch out. And we say, oh, look at on that oxygen, there's these lone pairs. And we know those lone pairs are going to make the oxygen bent. And that's still going to make that a polar molecule. So even though if it looks straight, if you see that there are lone pairs on the oxygen or on the nitrogen, that's going to make that molecule polar. So the bottom line is, if a molecule is very symmetrical, then it's going to end up being non-polar. So if it looks very even, it's non-polar. If it looks kind of off-center, then that's polar. But watch out for oxygen and nitrogen with those lone pairs. Those lone pairs make the molecule off-center even if you draw it very evenly.